I'm Nicholas Dwork. Today I'll be talking about a least squares optimal density compensation for gridding. Let's start with the Fourier transform. This is the definition of the Fourier transform that we'll be using in this presentation. Here, x is the space location and k is the frequency. If we assume that the spectrum of our signal is bounded, then we needn't integrate from negative infinity to infinity. We'll integrate from negative 0.5 to 0.5. We can approximate this integration with a Riemann sum, like so. And then if the frequency locations are evenly spaced, delta k, the spacing between frequency locations, is just equal to 1 over m. Just going to shift this equation at the top of the slide. And finally, if we only look at the integer locations in space, we can replace x with an index n. Now this is the inverse discrete Fourier transform. So what I've just shown is that the inverse discrete Fourier transform is a Riemann sum approximation to the inverse Fourier transform. And with Fourier sensing, this is how we make images. We take the Fourier domain, we partition it into a set of grids, we sample each grid location, and then we perform an inverse discrete Fourier transform to get an image. And one application of Fourier sensing is MRI, so this is an example of an MRI image reconstructed this way. But what if the data is not uniformly sampled on a grid? A common set of samples is a spiral readout, like shown here. In this case, what should the partition be? One guess is the Voronoi partition, like seen here. Now, that is a very reasonable thing to do, and it is often used with good results. The question we try to answer is, can we do better? Let's return to our approximation of the inverse Fourier transform. Here, the samples are no longer located on a grid. The key insight is that we don't actually need a partition. We only need to know the sizes of delta k sub n. This becomes the gridding algorithm, where we approximate the inverse discrete Fourier transform, where each Fourier value is weighted by w sub n. And so the question becomes, how can we find these density compensation values w? One answer is to look at the impulse response. The Fourier transform of the Dirac delta function is a constant 1, so the impulse response of gridding is what happens when we replace capital G with the constant function 1, like shown here. What impulse response do we want? Recall that the Dirac delta function is the identity value for the convolution operator. So if you have g, some function g, and you convolve it with delta, then you get back g. If we further assume that the image has compact support, and that the support is a subset of this rectangle n, then we don't actually need delta in the convolution operator. We can convolve g with delta hat and still get back the original function g, where delta hat is equal to delta when x is within twice the support region, and it doesn't matter what delta hat is outside of that region. So our goal is to choose values so that the point spread function approximates delta hat. Well, what does it mean to approximate the Dirac delta function? The function is concentrated near 0, it's as much like a sharp spike as possible, and it integrates to 1. So we're going to try and create density compensation values that lead to an impulse response that has these properties. And the values are going to be the result of an optimization problem. We're going to minimize the L2 norm of the impulse response over twice the field of view. Now, if we just leave it here, then this will set the weights to 0, and the function will be 0. It's true that the energy is minimized, but it doesn't do anything good. So what else can we do? We're going to set the value at the origin equal to some positive value r. This constraint will ensure that the weights do not yield the 0 function. We're further going to assume that all of the density compensation values are non-negative. This both makes the result of the optimization problem more stable and allows us to interpret these density compensation values as the sizes of the elements of a partition. It's much easier for an optimization algorithm to set the values far away from the origin to very low values than it is near the origin, because we've constrained the value of the origin to be positive. We can mitigate that by adding a weighting into the objective function like shown here. So this gets us a set of weights that give us the sort of behavior that we want. It's positive at the origin, it's small everywhere else, but it doesn't integrate to 1. Once we solve this problem, we'll scale w so that the integration over a region centered on the origin is 1. How do we solve this? If we set r equal to 1, the constraints require the set w to be an element of the probability simplex. And there are efficient computational algorithms for the proximal operator of the indicator function for elements of the probability simplex. Since we have the proximal operator for the constraints, if we can find the gradient of the objective function, then we can solve this problem with Fista. To find the gradient of the objective function means that we want to take the partial derivative with respect to each of the elements of W. Recall that this is the definition of the impulse response, so when we put this into the objective function, this is the expression of the partial derivative that we want. Calculation of that partial derivative is somewhat involved. I welcome you to review the manuscript for the details, but most amazingly, when you're done, the gradient of the objective function is a simple matrix multiplication with the vector W. Okay, so that gives us our optimization algorithm. We perform a gradient descent update, we project the result onto the probability simplex, and we use the momentum as specified by Fista. Note that that solution solves the following optimization problem, and in this sense, the solution is optimal. Here are 3 data where we're going to try out this algorithm. A shows a numerical phantom where I know the Fourier values exactly. B shows MRI data from the ISMRM Recon Challenge. And C shows data from the mridata.org website. For each of these data, we'll be using the radial, spiral, and propeller trajectories, respectively. Here are the results on the numerical phantom. Hopefully you can see that the error with the gradient projection algorithm is reduced in larger swaths of the image than in either the Voronoi or the fixed point iteration algorithms. Both are commonly used. Here are the results on the data from the 2010 ISMRM Recon Challenge, and again the same quality holds. And finally for the MRI data of the knee from mridata.org. Here we're showing what happens when you vary the parameter of the weighting in the objective function, and you see that significant details of the image are not gained or lost by varying the parameter by as much as 50%. In conclusion, we have developed a method for determining density compensation values that finds an optimal point spread function over a set with non-zero measure. Thank you for your attention.